In the last video, we finished the LED display. The last thing I want to do before we get to the circuit board is to see if we can use the 12 MHz onboard oscillator. We could then skip the 14.318 MHz parts. We can access the 12 MHz signal via the 12M pin, or we can also short this point to bring the 12 MHz signal directly to I/O pin 20. I purposefully used pin 20 for our 14.318 MHz external oscillator in case we wanted to use the short. I prefer to use an external jumper so we can switch between the two, and that's what I put on the breadboard. 12 MHz is pretty far from 14.318, so we can't just swap it, it won't work. Our 14.318 MHz oscillator is divided by 3.5 to produce about a 4.09 MHz pixel clock line. We can divide the 12 MHz oscillator by 3 to give us 4.00 MHz, which will produce a video out signal slightly closer to the NTSC spec. We're going to use a 4-stage register chain where every other stage is clocked on the opposite edge of the oscillator. The relative stepping between each Q output is therefore 1/2 clock cycle, so the Q0 output propagates through to the Q3 output in 4 1/2 clock steps. The trick here is using the inverted Q1 and Q3 outputs to feed D0. The rule is that when latches 1 and 3 are off, D0 turns on. At the start of a cycle, Q1 and Q3 will be off, so D0 will be on. The first positive oscillator edge at time 0 will therefore turn on Q0. On the next negative oscillator edge at time 1, latch 1 will copy Q0 and turn on Q1. At time 2, since the inverted Q1 is now low, D0 is low and the Q0 output drops. On that same rise of the oscillator edge at time 2, latch 2 copies Q1 and turns on Q2. At time 3, latch 1 copies the Q0 low, and latch 3 copies the Q2 high. At time 4, Q1 and Q3 are not both off, so D0 remains low and Q0 remains off. At time 5, Q1 copies the Q0 low and Q3 copies the Q2 low. On the rise of the next oscillator edge, D0 is on, raising Q0 and starting the whole cycle again. During 3 full oscillator cycles, Q0 is on for 1 cycle and off for 2, basically dividing the initial oscillator by 3 at a 33% duty cycle. Q1 through Q3 simply copy this pattern at a 1/2 oscillator offset. To get a nice 50% duty cycle, we simply OR Q0 and Q1 to get output P0. This output is considered glitch-free because Q0 and Q1 never transition at the same time, so there's no possibility of a glitch. We've basically divided the 12 MHz oscillator by 3 to get a nice 4 MHz signal at a 50% duty cycle for our pixel clock line. We also need to derive CKBH, which is at an offset from clock. We can generate 2 additional outputs offset by 1/3 of 4 MHz by ORing Q1 with Q2 and Q2 with Q3. Here, output P2 is close to the original offset of CKBH from clock, so we'll use output P0 for clock and P3 for CKBH. Output P1 will not be used in this design. Okay, let's wire this up. I'll add a divide by 3 module to the clocks file with 1 input and 3 phased outputs. We'll need 4 latches, then 4 always blocks on alternating edges. Yeah, we can combine the blocks, but the separation makes better self-documentation. And finally, we derive the 3 outputs. Copy that signature domain. I'll keep this near our low frequency stuff. We'll take in the oscillator line, and we're just using phase 0 and phase 2. Set clock and CKBH directly. And I need to disconnect the oscillator divider outputs. Forgot a semicolon there. Turn that on. And nothing. Oh, I need to change the jumper to the 12 megahertz line. Much better. Looks like nothing changed, which is good. Try out a few things. Credits accumulate. Start a one-player game. The most critical timing is for brick hits. Well, that works. The scoring and sounds seem to be working as well. Well, great, we can drive the system from the 12 megahertz oscillator. The last thing I want to do is have the system automatically switch between input frequencies instead of needing to modify code. If it senses 14.318 megahertz, it'll use the original oscillator divider, and if it senses 12 megahertz, it'll switch to the new divide by 3 module. I'll start a new speed test module that takes in the 10 kilohertz clock and the oscillator and tells us if the oscillator is 12 megahertz. This is specifically designed to work between our two source frequencies. What we're going to do is count oscillator pulses between 10 kilohertz clock transitions. The 12 megahertz oscillator will have about 600 cycles during the high or low portion of the 10 kilohertz clock, and the 14.318 megahertz oscillator will have about 716. We'll use the midpoint between these two values to determine which oscillator is active. Since the oscillator and 10 kilohertz clock inputs have an arbitrary and varying phase relationship, we need to buffer the state of the 10 kilohertz clock by running it through a synchronization register to remove metastability. Latch metastability occurs when data input changes while the clock is rising. This can produce glitches or oscillations that would ruin the count window. The extra latch removes any issues. We'll also need to keep track of the previous level of the 10 kilohertz line so we know when it transitions. And we'll need to count the oscillations. I'll start an always block on the fast clock and use that to sample the state of the slower clock. I'll first run the slower sampling clock through the synchronizing latch, then check if the sampling clock transitions. We sample during the high or low portion of the 10 kilohertz clock. The exclusive OR turns on when the values are different. We just need to know when it transitions for timing. If the sampling clock state just transitioned, we determine the speed output from the accumulated count, reset the counter, and copy the new sampling clock state. Otherwise, we need to bump the counter. And that's it. I'll copy that signature domain and connect it up. Just need a loose wire for that output. We can now select the proper divider outputs based on the speed test results. Make separate wires for the oscillator divider outputs and connect those up. Now that needs an underscore there. The last thing we can do is to show the sensed oscillator speed on that spare LED. Just need to modify the definition to accept the speed test output and add that to column 3. We can now move the jumper between the 12 MHz and 14.318 MHz oscillators, and the system automatically switches dividers. One thing I like about running on 12 MHz is that the pixel clock is now symmetrical. This makes the RGB to HDMI setup more stable since the phase relationship never changes. Well, wow, we're completely finished with both the external hardware and HDL for running Breakout from an FPGA, including using the onboard oscillator. We still needed 8 chips to interface with the outside world, but way better than 103. In the next video, we'll start on the circuit board for this. It may take a while, but I'll see you over there.